Okay, welcome everyone. So today it's a pleasure to welcome Yannis Liodakis. So Yannis did his undergrad and master's at the University of Patras, and then he moved here at the University of Crete, where he did his PhD. Actually, he obtained his PhD 4 years to this day, as I learned today. And then he moved to Stanford as a Kavli Fellow. He worked with Roger Romani there and Roger Blanford. And then since September 2020, he's a postdoctoral fellow at the Finnish Center for Astronomy with ESO in Finland. And he also holds a very prestigious Gruber Fellowship. And today, Yannis is going to talk to us about supermassive black holes and jets and polarization. So, Yanni, the stage is yours.
Well, hi, everyone. Thank you very much for the invitation and the kind introduction. I am a bit skeptical whether when you invited me, you did not know that this is exactly 4 years since my PhD defense. But if your purpose was to give me kind of flashbacks from those days, you're really succeeding, I have to say. So I thought I should discuss mostly things that happened after that defense, and I'll try to argue that polarization is indeed the way forward in understanding jets from supermassive black holes. And hopefully by the end I will have convinced you all. So we're fairly confident that every galaxy has a supermassive black hole in its center. The most compelling evidence, of course, comes from our own galaxy. And what I'm showing you here are the orbits of stars around a very massive and dark object in the center of the Milky Way, which we call Sagittarius A star. And this is our very own supermassive black hole. Now, these are very intriguing objects that we don't understand. And particularly, we don't understand why a very small fraction of those seem to launch very collimated and often highly relativistic streams of plasma that we call jets. So this is what a typical, I would say, galaxy with a jet looks like. For historical reason, we call them radio galaxies because they were first discovered in the radio. So what you see here is a bright spot in the center. Tell me if you cannot see my cursor. Here, we call that the AGN, which starts for active galactic nuclei. And the thin lines you see coming left and right from the AGN are the jets. And at the end, these giant structures that you see, we call them radial lobes. And this is basically where the jet terminates and is starting mixing with the intergalactic medium and is forming shocks. So if you focus in towards the AGN, this is what it looks like. The bright spot you see is what we call the core of the radio jet. And what's going outwards to the right, that's the main jet. There should be a very similar jet on the other side, which we call the counterjet. And somewhere between jet and counterjet is the supermassive black hole that is powering both of them. Now, radio galaxies are very nice objects that make very beautiful pictures, but they're relatively boring. I'm mostly interested in the subset of those radio galaxies that we call blazars. And these are sources where the jet is oriented towards our line of sight. So we're really looking down the barrel of the gun. And this actually is the reason why they have very interesting and very unique properties, I would say. So this is how typically we observe blazars in radio. So you will obviously notice that we've lost the beautiful two-jet structure. We now see only a bright spot, which we still call the core of the radio jet, although it doesn't really correspond to what we call the core of the jet in radio galaxies. And we also get a little bit of the jet. This is because they're not oriented exactly at 0 degrees from the line of sight. They're just a little bit, just a few degrees off axis. So that's why we get some of the jet too. So now that we've lost all the structure and can no longer resolve anything, the only way to study the sources is through their multi-wavelength emission. So there's been a lot of effort into that, and through blood, sweat, and tears, we've come up with different models of what we think blazars look like internally. I'm showing you here one of those models. There are many more. I would say this one is one of the most popular ones. And what you see is to the left, you have the supermassive black hole, which has an accretion disk, which is constantly feeding the black hole with gas. And then you have the jet that is being launched, and it goes, as it propagates outwards, goes through what we call the broadline region. These are basically clouds of gas that orbit the black hole. And this is where the emission lines we see in optical come from. And then the jet enters the region we call the acceleration region, where it's picking up speed, and until we reach the millimeter wave core. And this is thought to be a standing shock or a recollimation shock of the flow. This is what we think we're observing as the core of the radio jet, and that's where we have a lot of particle acceleration and a lot of the high energy emission coming from. And after you go through the core, then you enter a region where you're now in the parsec and kiloparsec scales, where radio dominates more and more of the emission. So if you look at M87, this is, you might already know, this is the image, the source that gave us the very famous image of the black hole. M87 is not really a radio galaxy, but it's not really a blazar either. It's kind of something in between. We often refer to this type of sources as misaligned AGN. So I'm showing you here images in radio, optical, and X-rays. And of course, the emission profile is a lot more complicated than the simplistic models that we have. But a lot of the structure is there. And in fact, there was a recent paper that studied how the jet structure evolves as the distance from the black hole, which you see here. And what they found is that the jet is initially parabolic, and RMHD simulations tell us that this is a shape that favors jet acceleration until the HST1 complex, which is also thought to be a standing shock, that happens to be close to the Bondi radius, which is basically where the sphere of influence of the black hole ends. And after that, it transitions into a conical geometry, which again, according to the simulations, that should not favor acceleration. So you shouldn't have any changes in the velocity after that, which pretty much matches what we have in our models for blazar. So this, it's highly encouraging. So what happens with the emission? Well, what I'm showing you here is what the spectral energy distribution of blazars looks like. There is a bit of diversity, of course, but they all have this, I would say, very characteristic two-hump shape. Some of the sources have their low energy hump peaking at the infrared, and we call those low peak sources. Some have it peaking in the optical, which are intermediate, and of course, some in the X-rays, which we call high peak sources. And there also seems to be an anticorrelation between the brightness of the source with the peak of the low energy emission. There are few physical interpretations for that, whether this is real or not. This is, I would say, a matter of a very vivid debate at the moment. So we think that the low energy emission is synchrotron radiation from relativistic electrons that are being accelerated in the magnetic field of the jet. There are a few evidence for that, but the strongest we have comes from polarization. So in the laboratory, you would just put a filter in front of the light source, and that filter will block certain directions of the incoming light and will give rise to linear polarization. Nature kind of does that with magnetic fields. And in this particular setting, you have particles that are moving along magnetic field lines, and that gives them a preferred direction of emission, which also gives rise to linear polarization. So if you have a population of electrons with a parallel distribution of energies, and you've put them in a very ordered magnetic field, then the maximum polarization you get is about 70%. We have observed, I think, up to 45% polarization in blazars. So if you take into account that you're looking at the parsec scale jet, and magnetic field is not perfectly ordered, this is basically as good as it can get. And of course, in this particular setting, there is no other mechanism other than synchrotron emission that can give you as high polarization. Of course, this happens in exceptional cases. Most typically, what we observe is about 10% polarization. And this is an example I'm showing you here from one of the sources that we were monitoring with RoboPol at Skinegas Observatory. And what you see is the top panel is the polarization degree, the middle is the polarization angle, and the bottom has the R band magnetic flux. So polarization signatures in blazars are fairly complicated. There seem to be mostly stochastic, but for reasons we don't fully understand, there are periods in time where we see this peculiar, I would say, coherent motions of the polarization plane towards one direction. And this is what you're seeing in red. We call those EVPA rotations, and it's basically one of the main science drives for OPAL. But there are a few other weird polarization behaviors that we observe in blazars, but all of them seem to have a very strong connection to the internal processes of the jet, and also to the processes that make high energy emission. And just to give you a few of the results from the RoboPol survey that are, I would say, very related to that, is one of them is that we found that sources that make gamma rays, or at least sources that make enough gamma rays for the Fermi Gamma Ray Telescope to detect them, seem to be a lot more polarized than the sources that don't make gamma rays. We also find evidence for an anticorrelation between the polarization degree and the peak of the low energy emission. And of course, one of the most striking results was that there seems to be a very strong connection in time between the EVPA rotations and gamma ray flares. So that all tells us that there is definitely a strong relation between what's driving variations in the magnetic field with high energy emission. So most recently, we studied two particular events in one source called C345.3. This is one of the brightest sources in gamma rays. And these two events kind of caught our eye. And you will understand why shortly. This one happened in late 2013, where the source was in a relatively quiescent state for several months. As you might notice in the top panel, which is the gamma ray light curve, there's a lot of these red points, which are upper limits. So one of the most brightest sources in the gamma ray sky was not detected for an extended period of time. And then suddenly it goes through this very clean, I would say, rather beautiful outburst that we see across the electromagnetic spectrum. So the top panel, as I said, is gamma rays. Then you have X-rays, optical, infrared, the polarization degree, and then the polarization angle. So at peak, the polarization degree in that source was 30%, which is not the record holder, 45, but it's still the most polarized the source has been in the past 10 years. So that's actually one of the things that really caught our eye. So the source, as I said, was quiescent, had an outburst, and then went back to quiescent as if nothing really ever happened. And then a few months later, we saw this event, which is a much brighter event. It's a bit more complicated now because you see there's no one peak structure, there are multiple peaks, but they, at least the optical and gamma rays, seem to follow each other closely. We also find peculiar polarization behavior. There is a flare, which now goes to 20%, but it doesn't really align itself with the flares in the optical or gamma rays. And then from 20%, within a matter of a couple of days, it drops down to 0. And then suddenly goes back again to about 10 and just fluctuates after that stochastically. At the same time, the polarization was dropping from 20 to 0. We see this very beautiful 230-degree rotation. So at the first glance, you might say, well, these are very different, two very different events, and they're kind of unrelated. There's a very different story for each one of them. And this is actually what we thought initially, but then we started finding evidence that we're actually looking at exactly the same thing that just manifests itself differently. And our strongest evidence comes from BLBI observations, which you see here. This is basically different components and with the radium maps that were detected as a function of time, basically. So the interesting component here is this component C, and this is supposed to be a stationary component. So its distance with respect to the core versus time should not change. But what we see here is that there is an inward motion. Basically, that stationary feature is falling back towards the black hole, which is not really possible. What's really happening is that there is something that's moving outwards, but is still under the resolution. So since you cannot resolve it, you see a displacement in the emission of the core. And because you measure everything with respect to that, you see this inward motion. So when what was moving under the resolution was K14, which you see here, was ejected, then component C moved back to its original position. So the ejection of K14 coincides, of course, with this flare in early 2014. So we can put all of this together in a very simple picture where you have a traveling shock, and that shock moves down the jet, and for some reason there is a kink in the jet, there's some bend, there is some motion, helical motion that slightly changes the orientation towards the line of sight of that shock, and it gives this beautiful flare. And as it moves away slightly from our line of sight, we're talking just a couple of degrees, not big changes, but because of this relativistic effects, any small change manifests itself very strongly. So just a few degrees shift can make this beautiful flare, and then goes back to quiescent. And then as soon as it hits the standing shock, it produces this flare. And of course, the polarization behavior that we see here is very consistent with two components with varying fluxes and a different polarization angle that can pretty much explain everything. So we're now certain that what we see in blazars obviously is more than meets the eye, but we have strong evidence that at least one of the mechanisms for the EVP rotations is crossings of the standing shock. So before I move any further, I'll just pause and take questions here, because then I'm slightly changing the topic. Are there any questions? I cannot see if there are any hands raised because of the shared screen. If somebody can help. Oh.
So there are no hands raised, Yannis.
Okay, then I'll just move on then. So what happens with the high energy emission? So this is something that we really struggle with. And it's particularly important because it tells us something about the composition of the jet and the jet formation mechanism. And at least in this kind of system, this is impossible to directly observe. So it's very important. And there are basically two schools of thought here. One of them is that you have a paraplasma. This is just electrons and positrons, and those will make high energy emission through inverse Compton scattering. This is what we call leptonic processes. So basically, electrons move down the jet, they see some target photon field, and they upscatter it to higher energies. The other school of thought has an ion composition. So you have protons in your jet, and protons will make proton synchrotron. And after they cross some energy threshold, they start to make pairs and pions, which then decay to secondary particles and gamma rays. So you can imagine there's been a lot of work in trying to differentiate these two processes, but unfortunately, we have not been very successful. And one of the reasons is that a lot of this work has been driven mainly by SCD modeling. And the example I'm showing you here, you can clearly see that there are two different, I would say very different models that can produce a fairly similar fit to the data. This is, of course, because the models are highly complex, and the coverage we have across frequencies is often not good. It's not that we don't learn a lot from ICD modeling. It has not been very conclusive. So you can imagine the excitement the community had a few years ago when the IceCube Neutrino Observatory in the South Pole detected a high energy astrophysical neutrino. It was a few hundred TeV coming from the direction of a blazar that's also seemed to be flaring at the time. Now, there's been a lot of discussion in the community, and there's a lot of people have disputed this association, and for some good reasons that I will not go into at the moment, but it was still exciting enough to get people working on that source and coming up with models and try to understand it. And this is actually where we start to run into trouble. So on the left, what you see is a leptonic model, which gives a very nice fit to the data, but leptons don't make neutrinos. On the right-hand side, there is a purely hadronic model, which can easily make neutrinos, but it grossly overproduces the X-rays and the MEV emission from that source. So that's not really working either. So people are trying to come up with different configurations and what they call hybrid models or leptohadronic in order to try and explain it. What I'm showing you here is a small subset of these models that basically Google search just gave me. There are plenty more out there, and my apologies if your favorite one is not listed here. But that's just to show you, all the effort has been going on into trying to understand this event. And I think it's fair to say that we have a lot more questions than we have answers after this event. So while everybody was working on that, we thought we should be going in a different direction. And there is a fairly clear and testable prediction of these leptonic models that because it's inverse Compton scattering, you should have a strong correlation between the low and the high energies. So we gathered up all the data that we could find in optical and gamma rays, and we came up with 178 sources, which is about 20 times more than any sample that anyone has ever looked at in that way. And we try to playing a game where we're shifting one light curve with respect to the other and trying to find where a correlation coefficient is maximized in time. And this is the example you see here. So if you do that for all 178 sources, this is what you will find. This shows the significance of that correlation versus the time difference that we find as the best correlation. And I think it's obvious that there's a very strong trend for simultaneous variations between optical and gamma rays. And what is particularly important is it doesn't matter how you split your sample, you still come up with this strong preference. So this seems to be a universal feature in blazars, and it argues very strongly in favor of leptonic processes. But we wanted to take it a little bit a step further and look at what individual flares are doing. And we're particularly interested in what we call orphan flares. These are flares we see in gamma rays, but they don't seem to have an optical counterpart. So what I'm showing you here is just what we call a Bayesian block representation of the light curve, which helps us identify these flares. And then we play a different game where we try to match the flares we see in the optical with the flares we see in gamma rays. Of course, there's a lot of gruesome details that I'm going to spare you. But the end result is basically that roughly 1 in 5 gamma ray flares seem to be orphan. Now, that's of course not a lot, but in the very standard leptonic models, those should not exist at all. Of course, you can have different geometries, you can have different magnetic field configurations that will also produce orphan flares within a leptonic setting. But it's of course much easier if you just have a small population of protons that occasionally does something. So the question is, can we figure this out? Can we do better? And the answer is, of course, yes. And again, polarization has the answers. And this time is high energy polarization. So the example I'm showing you here in the bottom panel, you see again 2 different models that produce a very similar fit to the data. But in the top panel, this is the prediction of what the polarization should look like for these different models. And you can see these are very different, and they're especially different in the X-ray regime. So unfortunately, so far, we didn't have the opportunity to test these predictions because there was no instrument to produce high energy polarization measurements. But of course, this is all about to change because NASA finally has approved the first ever X-ray polarization mission that will target blazars. It's called IXPE, or stands for the Imaging X-ray Polarimeter Explorer. It's a small NASA mission, so it's only has a 2-year lifetime, but we're obviously hoping for an extension. It's going to be working in the 1 to 10 kV band. And I'm very happy to say that it's approved and will be launched sometime in October this year. So it will be a very, very exciting time, and we've been working very hard in trying and choosing the right targets that will allow us to achieve our scientific objectives. And this is a work I did with a graduate student at Stanford called Lawrence Pearson, looking at what we call multi-zone jet models. And this is an example. Here, what you see, this is the cross-section of the jet, and the different circles are different emission regions, or different zones, as we call them, that have their own population of electrons and their own magnetic field configuration. So what you get from such a model is the sum of all the zones that contribute to the emission, and the polarization is the maximum polarization you get from synchronon, which, as I told you, is 70%, scaled down by the square root of n, where n is the number of zones that contribute to that emission. And also, so let me play that animation for you. This is also a way to produce AVPA rotations that Lawrence is currently working on with this type of models. So basically, using these models, you can get a prediction of what the polarization is doing across the synchrotron spectrum. And then if you have measurements, for example, in the optical, which we do with Robopol, you can take that synchrotron polarization spectrum and scale it in for different sources. And then you can use that to make predictions of what the X-ray polarization would look like. And this is exactly what you see here. It shows the predicted X-ray polarization degree versus the flux. And the red dashed lines are is the sensitivity limit of YXP for different exposure times. This all was made assuming a leptonic model. If something else is happening, most likely if we have proton synchrotron, then all the black points you see there are going to be higher by a factor of 3, basically. So a few of them will be in the 100 kilosecond range, which is going to be kind of a typical exposure for IXP. So we've actually designed our program to achieve all our scientific objectives and put strong constraints in these emission processes, even at the first year of IXP. I would like to be surprised, but my prediction is that we're not going to see anything different than the plot you're seeing here, and that the X-ray emission will most likely be inverse Koplan scattering. There are a few reasons for that, but most recently, we had a paper with Maria Petropoulou where we asked a fairly simple question, and that was, are blazars energetic enough to have all of their high energy emission produced by proton synchrotron, which is, among all these hadronic models, is the least energetically demanding one, and it's a lot more energetically demanding than any leptonic model. So the first thing we looked at was, what is the state of our sources now? So what you're seeing here is the magnetic flux versus the accretion disk luminosity times the black hole mass. And the dashed line is the prediction from what we call the MAD regime. MAD stands for magnetically arrested disk, and it's the regime where the sources extract the most energy out of the black hole that sometimes can go out more than 100%. So as you can see, all the sources are very close to that MAD prediction, which tells us that blazars are pretty much extracting all of the energy that can be extracting at the moment. So then we estimated what is the minimum jet power that you need in order for proton synchrotron to make all of the high energy emission that we observe. And we compare that with different, I would say, very standard energy estimators like, Eddington luminosity, the accretion disk luminosity, and the power that you get from the Blanford-Snike mechanism, which is another very efficient mechanism of extracting energy from the spin of the black hole. So I'm showing you here the comparison with the Blanford-Snike power, but all the other comparisons are qualitatively the same. So the solid black line, you see, this is equality. The dashed black line, where most sources seem to cluster, is 2 orders of magnitude higher. So that really tells us that you require basically 2 orders of magnitude, that it's available in your system, and you're already extracting as all the energy you could possibly extract. So it's rather unlikely that proton synchrotron is responsible for the high energy emission that we see in blazars. Of course, we're unfortunately not done yet, because what we're looking here is the steady state emission. We cannot really exclude occasions where you have some flare where protons are dominating the emission, and this really goes back to the orphan flaring that I told you earlier. Of course, there are other reasons. One of them is this leptohadronic models that I've mentioned, where the protons are subdominant in their emission. Now the proton contribution you see here is in blue, and it only really manifests itself in the very high energy TV gamma rays, which are absorbed by the extragalactic background light, and also in the X-ray band, but only in this particular sources, which these are the intermediate peak sources I told you about, where the X-rays fall in this valley between the synchrotron and the Compton emission, where the leptonic emission is pretty much suppressed. This, of course, does provide us with a great opportunity, because the X-ray band is where IXP will be looking at. Unfortunately, this source is relatively faint and not very polarized. It's not really a good candidate target for IXP, but don't despair just yet, because we've been working very hard to find other sources that kind of fit the bill, and we were fairly lucky that one of them is 0716, which has already been identified as a good candidate for IXP. And what you see here at the bottom panel is a joint Swift and NuStar observation, where you clearly see this kind of transition between the low and the high energy component. And if you model that with the multi-zone jet models I told you earlier, you can get what the polarization will do across the IXP band, which is shown with the magenta lines. So what we find is that there is a struggle between the increasing synchrotron polarization and the relatively unpolarized Compton emission, leading to a steady decrease in the polarization degree across the IXP band. And if the low and the high energy components have a different polarization angle, you also expect to see a flip. If, on the other hand, proton synchrotron is dominating in that area, then we will see something that's very different. But first of all, it will be much more polarized. There's no reason or no indication that there will be a change in the polarization across the XP band, and we certainly don't expect to see a change in the polarization angle. So this is another clear signature that we can look for and test at the time of the IXP observation. Very recently, we got 60 kilosecond of XMM time to do J0211, which is the other candidate source that we've identified for IXP. And what you see here in black is the archival observation, and blue we have the new XMM data. So in this process of now modeling this source, but we should be ready by October, where IXP launch, and we're going to know what to expect. Of course, if IXP is not good enough for the task at hand, there is EXTP coming. This is a Chinese-led mission that will launch in 2025 after at least nominal end of the IXP mission. And we've already put out a white paper on XPP, which stands for X-ray polarization probe, and that hopefully will be NASA's next high energy polarization mission, which hopefully will also be a broadband X-ray polarimeter. There's also a European led mission called Astrogam, and an American one called Amigo, and these are going to be MEV polarimeters, and we're also expecting to see some very interesting polarization behavior in those energies as well. So just to summarize, I hope I convinced you that jets are very exciting, very interesting. Cosmic laboratories and polarization is a great way to understand them and understand their internal processes. Of course, there is still a lot to learn, but hopefully, if IXP doesn't blow up during launch, we're going to have answers to at least a few questions fairly certain. And hopefully next time when we have those answers, I can come in person and tell you all about them. Thank you very much.
Well, thank you very much, Yanni, for the super exciting presentation. Are there any questions for Yannis? Please either use the chat or raise your hands or just simply speak up. Or perhaps I can ask a simple one to get things started. So you said that EXTP will probably launch in the 2025. Is that right? So
yes.
So is this designed to cover the same band as the IXP, or is it a different?
Yes, it's exactly the same in terms of detectors. It's just 3 times bigger. So by the same team in Italy that made IXP is also providing the same detectors for EXTP. It just be more sensitive and better.
Okay, thanks. I see a question, hand raised by Vaso. So Vaso, please pick up.
Thank you, Yanni, and other Yanni. Speaker Yanni, I thought it was a very interesting result about the proton synchrotron not being a go for most blazars due to energetics requirement, especially given that, at some extent, we know that nature somehow makes accelerated protons, because we see the protons themselves. So I guess my question is, do you think we could calculate, given the same energetic constraints that you calculated, how many protons could really be accelerated by blazars without I mean, is it just these 2 orders of magnitude below, all of them? And what would this translate in terms of proton flux available in the universe, so that we could compare it with other useful things like cosmic ray fluxes or neutrino fluxes or things like that before we run into energetic troubles?
So the estimates we have here basically assume that you have 1 proton per electron. I think this is not necessarily the case. So that should be, I'm not entirely out of the top of my head, I don't know exactly how that will affect what you're discussing, but I think we definitely have, I mean, this is a way you can get the proton flux out of, so in principle, yes, we can do this exercise.
Thank you, Vaso. Thank you, Yannis. Other questions? Please just speak up. Well, perhaps I have yet another naive question, Yanni. So you at some point you mentioned that there are no orphan flares expected in the leptonic model. Could you perhaps elaborate a bit more on that? I mean, is there any estimate on how one could get such an orphan flare in the leptonic model, or is no chance?
So there are different models for that. One, again, I would say popular one is called the Ring of Fire, where basically you have a concentration of gas in certain areas of the jet, and then as a shock goes through it, you don't really excite more particles, so you won't see any optical emission, but you suddenly increase the target photon field, so that will give you a gamma ray flare. So that's one of them. There are other models involving magnetic field configurations that will basically either kind of suppress or move away from your line of sight the optical emission, but still produce gamma rays. But these are a lot more complicated and maybe not as physical. But I think this Ring of Fire model could be one of the one reasonable explanation for it.
I have a question, Yannis. My name is Lucas Lajos. That's a nice talk, excellent talk. But probably the question comes from the naive part of my understanding, and that was once we have uncertainties on the acceleration of particles and who is dominating in the emission, and then we have uncertainties on the structure of the magnetic field. The polarization seems to be dancing between many uncertainties. How can you fix some of this? For example, how can you fix the structure of the magnetic field in this case?
That's a very good question. You cannot. So basically what we're looking at is relative differences. So for example, simply having an X-ray polarization measurement doesn't tell us anything at all. We need to know what's happening in all other bands and try to figure out how, you know, you can go from one model to the other and make your case, which is the strongest one, which is the more likely one.
Mm-hmm.
But yeah, it's something that we're really struggling with, and there is actually a lot of effort that I did not mention of preparing this, I would say, gigantic multi-wavelength campaign to focus on the IXP blazars when they're observed.
Mm-hmm. Yeah, the main game is the magnetic field, of course. I mean, the magnetic field, if it's turbulent, it has to be needed some orientation structures or some structural forms to give you, to enhance the polarization. Otherwise, it drops due to the stochastic motion. It drops the polarization very much. So, okay, but you're right. We have to fix one of these two parameters, especially if the energetic particles and the magnetic field are actually getting, working together. This is the point.
So we're hoping to learn a lot more on that magnetic field and in the acceleration process from the high synchrotron peak sources. So this is where radio optical and X-rays are all part of the same synchrotron spectrum. So we're hoping, and there's predictions from magnetic reconnection models and shock models of what we expect to see in terms of the polarization degree and polarization angle changing across the synchrotron spectrum. So we're hoping that those will kind of guide us into learning about these acceleration processes more. And then the low peak sources will tell us about something about the composition of the jet and the mechanism for the high energy emission.
Thank you very much. That's clear. Thank you very much.
Well,
hi, Yannis.
Yannis?
Yes, I have. Can you hear me?
Yes, I
yes,
can.
we can hear you.
Okay. So very nice talk, Yannis. Thank you. I have two IXP related questions, two short ones. The first one is, what is the accuracy expected in polarization, and is it flux dependent? And the second one is, do we expect the polarization measurements to come in as soon as the satellite flies, or is there any lag? So some calibration procedure at first or something like this before we start getting the data?
So it depends both on the flux, but also the polarization state. So it actually depends a lot more on the polarization. So if you have a highly polarized source, it would be a lot easier if it's not that bright, actually. So I think the mission requirements is that we have a 5% minimum detectable polarization for 10 to the 11 to 10 to the minus 11 ergs per second per centimeter square source in 100 kiloseconds. If that kind of helps you put any, make any visual images of that. But there is already a tool online that you can find where you can plug in values for your sources, and that will tell you what is the minimum polarization you can detect in what exposure time with IXP. Now, on their second question, we expect the measurements to be out fairly soon. There's going to be, I would say, a few days or maybe a couple of weeks of calibration just to make sure that everything runs smoothly. But after that, the data is going to coming in, and what is very important, I would say, for the community is that the data, there's no proprietary period, and that the data would be immediately public to everyone to use.
Okay, thank you. Thank you, Yannis.
Other questions for Yannis? If not, then let's thank Yannis again for the excellent talk, and thank you all for attending, and see you next time. Bye, everyone.